Welcome back to AP Chemistry. In this lesson, we're going to be looking at reactions between strong acids and weak bases. Now, in a previous video, we looked at strong bases and weak acids, and in a video before that, we looked at strong acids and weak acids. And so this is the third of those combinations that we're going to be looking at in this course. So here's an example of a case where you'd have a strong acid and a weak base. A solution of hydrochloric acid is being added dropwise to a beaker of ammonia. Well, whenever you do this, you always want to represent the strong acid as an H+. And so you're always going to want to use H+, whether it's hydrochloric or any other strong acid. Now, the weak base should always be written using its full formula. So ammonia solution is NH3. So we're going to add these together like this. Now, the easiest way to write the formula for the product is just add these two reactants together. So when you combine those, you're going to get ammonium ion, NH4 positive. And so pretty much everything else is going to be a spectator ion. So in the strong acid, we have hydrochloric. So that means that the Cl negative, the chloride ion, would be the spectator in that particular reaction. Let's look at an example here where we're going to have to find the pH. Here we have a student adding 80.0 milliliters of 0.100 molar nitric acid to 125 milliliters of 0.120 molar ammonia solution. So the first part says give the net ionic equation. Well, when we realize that we're adding a strong acid, we should write that as H+, and then the weak base ammonia is just NH3, so we're going to combine it just like we did in the other example. Now part B, the spectator ions, hopefully we can see that the nitrate, NO3, is going to be the spectator ion in here. So for part C, determining the pH, we're going to have to, first of all, calculate that using an icebox. Anytime we have a strong acid or a strong base involved, we have to use moles in this because we assume it goes to completion. So we're going to use a mole icebox, and so here we have ICE. And so the moles of H+ would be 0.100 molar times 0.08 liters. So when we multiply those by each other, we get 0.008 moles of hydrogen ions. For ammonia, we'll do the same thing. We take the 0.120 molar times 0.125 liters, and when we multiply that, we should get an answer of about 0.015 moles. Now, starting out, we don't have any ammonium ion, so we're going to call that 0. And looking at the reactants, we can see that there's less hydrogen ion, so that's going to be the limiting reactants. We can subtract 0.008 moles from both of those reactants, and that means that we're going to add 0.008 moles to the product side, to the ammonium ion. So the hydrogen has been depleted, and so our number of moles of ammonia would be 0.007, and for ammonium would be 0.008. Now, of course, since we look at the solution here, we have all the acid has been used up, and we still have excess base here, so that tells us that this reaction or this solution is going to be basic after we've combined these two. Well, to figure out the pH, we have to take these two values here and find the actual concentration in moles per liter. So we're going to have to divide both of those values by the total volume. Now, the total volume is just adding the 80 milliliters to the 125 milliliters. That's 205 milliliters, or 0.205 liters. So we do that for ammonia, and we get 0.0341 molar, and we take the 0.008 moles of ammonium ion and divide that by the volume, and we also get about 0.0390 molar for that. Now, since this is a weak base problem, we're going to set this up as a KB. We're actually going to write the dissociation for ammonia, and we're going to have to plug these two numbers here into that ice box. And so the dissociation of ammonia looks something like this. And so we're just going to put those numbers in there. The ammonia would be 0.0341. The ammonium is 0.0390. And we don't really have any hydroxide to speak of, so that's a 0. And we know that the product side will have to go up since there's a 0 over here. So these will be plus X, and the reactant side would have to be a minus X in that case, plus X over here. And so we can see our equilibrium values. And so now we can take these three equilibrium values and plug them into the Kb expression for this reaction. And so we'll do that. And here's the ice box again. So there's the Kb expression, and we plug those values in. By the way, the Kb value for ammonia is 1.8 times 10 to the negative fifth. That's a number that will normally be given to you in a homework problem or on a test, or it's a number that you can look up pretty easily as well. Now we notice that this is a small equilibrium constant, and we don't like quadratic equations, and so let's obliterate the plus x there and the minus x here to get rid of those. And now we can cross multiply and solve for x. And the answer I get is that x equals about 1.57 times 10 to the negative fifth. Now looking back to our icebox, we can see that the significance of x is that that is the hydroxide ion concentration. And if we know the hydroxide ion concentration, then it's pretty easy to take negative log of that and find the pOH. So we can do that, and the pOH is about 4.80. And at this point, all we have to do to find pH is just subtract that number from 14. So when you do that, we get that the pH is about 9.20. And that makes sense because it should be a basic pH, and this is on the basic side. Well, let's try something else here, because we notice that in this example, and in one of the examples in the previous video as well, we had a mixture of a conjugate base along with its weak acid from which it comes from. So for example, we have ammonium here, NH4+. That's a weak acid, technically. And then the ammonia, NH3, is its conjugate base. And we had that in the previous video as well. Anytime we have the mixture of a weak acid and its conjugate base, we actually have what's called a buffer. Now, a buffer has a very special chemical property. Since it has a weak acid and its conjugate base, it tends to resist pH change. And so you can add a little bit of even strong base or strong acid to it, and it's not going to change its pH very much. And we'll see an example of that here shortly. A good example of a buffer would be found in your blood. You have a buffer inside your blood that maintains your pH around 7.4. That's a physiological pH in the human body. So that means that you can drink a Coca-Cola, for example, which has a pH of less than 3, and it's not going to give you acidosis and hurt you in the long run. So if you see a solution that has a weak acid and a conjugate base, you know it's a buffer. So how about this? Would this mixture here form a buffer? Well, I hope you say no. That's a no. Now the reason is that H2SO4, sulfuric acid, is not a weak acid. That is a strong acid. And very specifically, it has to be a weak acid. And we have a conjugate base, but that's not a weak acid, so that doesn't count. Now how about this one? Hopefully you give a strong no on that one as well, because we have a strong base and a weak base. So there's no strong acid here at all, so that's definitely a no. And on the third example, we have acetic acid, and that is a weak acid, and it seems like we have its conjugate base here as well. So that is a yes. We do have a buffer here in this example, so it's just that one. Now let's try an example with calculating the pH of a buffer, and actually these are pretty simple. If you're able to calculate the pH of a weak acid, you can calculate the pH of a buffer. So here we have a buffer with 0.60 molar hydrofluoric acid and 0.20 molar sodium fluoride. So let's calculate the pH of that. Well, the first thing we have to do is recognize that the sodium here that's on the front of the fluoride is just a spectator ion, and so it's not going to do anything. So if we realize that, we realize this is just a weak acid problem. We're going to write the dissociation of HF, and so it looks like that. We've done that before, and we're going to solve this as an icebox problem. And these numbers just go right into the icebox. The concentration of HF is 0.60, and the concentration of the hydronium is essentially 0 here, and the fluoride is 0.20. So those get plugged in. We know that this side, the product side, will have to go up because there's a 0 here. So the reactant side has to be a minus X, and the product side would be plus X on both of those. So here are your equilibrium values. So now we can take these values for equilibrium and plug those into the Ka expression for HF. And so hopefully you can write a Ka that looks something like this, and then plug in those values. We don't like quadratic equations, so we're going to obliterate the plus x and minus x, hoping that they're very small. And now we can cross multiply and solve for x. And when we do that, I get an answer that x equals about 0.00216. And if we know the x value, well, that's basically H plus according to the problem. So if we know the H plus, then we can just take negative log of that and find the pH pretty easily, which is about 2.66. And so this is a way to work a buffer problem and find the pH of a buffer. Now, in a previous video, I mentioned that there is a shortcut for solving these buffer problems or solving problems like this. So, do you like shortcuts? And I imagine that you do. Well, we're going to work the same problem, except we're going to use an equation. And the equation is the Henderson-Hasselbalch equation. And it's used to solve for pH. Now, pH, as we've learned earlier on, is the negative log of, well, H. So that means that pKa would just be the negative log of the Ka value of that acid. Now, the A negative, that is the concentration of the conjugate base, where that A negative is just the generic formula for any conjugate base. And then the HA is the concentration of the weak acid, where HA is just some generic weak acid. And so all we have to do is plug into the equation here. We know that Ka is 7.2 times 10 to the negative fourth for this acid. And we're going to plug these in here. Now, the negative log of the Ka is about 3.14, and 0.2 divided by 0.6 would be 1/3. The log of 1/3 is actually negative 0.48. So when we do the math on this, we find that the pH of the buffer is 2.66, and that's exactly what we said it was when we worked this using the much longer method. And so let's take this buffer here, and we're going to do something to it. So let's take the buffer. We'll do one more problem here, solving a buffer problem. And this time, we're going to take this same buffer, this buffer that's made from 0.60 molar HF, hydrofluoric acid, and 0.20 molar sodium fluoride. And we're going to have a chemist that obtains 250 milliliters of this buffer, and we just said the pH is 2.66, and we're going to add something to it. We're going to add 0.040 moles of solid sodium hydroxide. So that is some really basic stuff. Let's find the pH after we do that. Now, we're going to assume that there's no volume change, that by adding the solid sodium hydroxide, it's not going to change the 250 milliliters by any significant amount, which is a big assumption, but we're going to make that. So the first thing that we want to do, since we have a strong base right here that's reacting with an acid, we're going to have to write the equation for that. So the hydroxide, OH negative, is going to react with an acid. Bases always react with acids. And so hydroxide, OH negative, will react with HF. Okay? So we're going to write HF plus OH negative. And we know that this is an acid, so one of the products has to be the conjugate base, which is F negative, fluoride. And for the base, the other product has to be the conjugate acid of that, which is water. So those are our two products. Now, let's figure out the moles. Anytime we have a strong acid or a strong base reacting, we have to figure out the moles. So an ice box is the easiest way for that. And so we'll start with the acid here. We have 0.60 molar acid, and we have 0.250 liters of that. So when you multiply that out, we should get that it is about 0.15 moles of the hydrofluoric acid. And we'll do the same thing for the hydroxide. We have 0.04 moles of that. We'll add that in here in a second. The fluoride, we have 0.20 moles of the fluoride. And once again, it's 0.25 liters of that. So when you multiply that out, it's 0.05 moles of fluoride. And like I said a second ago, the problem comes right out and tells us we're adding 0.04 moles of the hydroxide. So we'll add that in. Now, which one of these two is going to run out first? Hopefully you can see that it's the hydroxide. There's less of it. So the hydroxide is the limiting reactant here. So both of these go down by 0.04 moles. That means that the fluoride goes up by 0.04 moles. And so for hydrofluoric acid, we'll have 0.11 moles. Hydroxide is gone. And we have 0.09 moles of fluoride. Now, to figure out the actual pH, we need to convert these to molarity. So we're going to divide both of these numbers by the total volume. And we just said the total volume is this 250 milliliters, or 0.25 liters. So we do that for HF. It's 0.11 moles divided by the volume, which we said was 0.250 liters, which gives us a molarity of 0.440 molar. We do the same thing for the fluoride concentration. We said it was 0.09 moles divided by the total volume, and so that gives us 0.360 molar. And so now we have a couple different ways to solve the problem. We can plug this into an ice box, or if you prefer, you can use the Henderson-Hasselbalch equation. It doesn't matter. Let's try the long way first and see what happens. If we write this as a dissociation of HF and plug those into the ice box, we have the ice box here. Plug these numbers in, 0.44 molar, 0.36 molar, and 0 for the hydronium. We have minus X, and plus X. We get those values for equilibrium. We can now take these values and plug them into the equilibrium constant expression for the dissociation of HF. So it would look like that. And then we plug these numbers in. And of course, we would obliterate the plus X and minus X because those are very small. And we solve for X, and we get 8.8 times 10 to the negative fourth. And looking at the problem, X is the hydronium, or the H+. So if we just take the negative log of that, it gives us the pH, and that would be 3.05. Now, that's a lot of work. We could use the Henderson-Hasselbalch equation. So if you don't like that second ice box, then you can plug it in here. And so we plug these numbers in, and we end up getting 3.14 as the pKa for this here. And the log of 0.36 over 0.44 would be negative 0.09. And look at that. You got the exact same answer, 3.05. And so we have a shortcut here for working any of these problems where that second ice box is involved, that the weak acid and its conjugate base. Now these problems are pretty long, and short of using the Henderson-Hasselbalch equation, there's not a whole lot to shorten these. These are just tough. You have to do some practice, have to do several of these to get a lot better at them. Well, I hope that this video was able to make this very complex problem a little bit easier for you. And if you understood it, and if you learned something from this, then I hope you give me a thumbs up. I hope you subscribe to my channel, and I hope to see you again in the future where we can learn some more chemistry together.